A variation on the stagnation tube that is used frequently to measure fluid velocity in the case where we have a closed tank or pipe with flowing water is called a pitot tube. Pitot tube consists of two piezometric tubes. One is built on the stagnation point. That's the blue water I'm showing here. The second has its outlet actually in the lateral surface of the tube and does not have a stagnation point associated with it. If I define the points at these entrances to be point 1 to the lower entrance and point 2 to the upper, and then I'm going to define point 0 to be over here to the left. And I'm going to use the Bernoulli equation from 0 to 2, and I'm going to use it from 0 to 1. Now, as we introduced in class today, we said that we apply the Bernoulli equation along a streamline. So how can we have two streamlines going from point 0? Well, let's sketch this in red. The stagnation streamline goes immediately from 0 to 2. Now, if we move just an infinitesimal distance below that point, if that's above, below that point, that streamline has to move around the lower edge of the tube. And so those 2 points far upstream coincide at point 0. So I can apply it from 0 to 1, I can apply it from 0 to 2, therefore I can apply it from 1 to 2. Now more generally, when we introduce the idea of irrotational flow, I'll justify the use of the Bernoulli equation like this a little bit more broadly. But for now I'm just going to set it up going from point 1 to point 2. So P1 over gamma plus Z1 plus V1 squared over 2G is equal to P2 over gamma plus Z2 plus V2 squared over 2G. Now, V1, note that V1 is equal to the approach velocity V0, that it's the same velocity that's going by upstream, and the velocity at point 2 is equal to 0 because it's in the stagnation point on that stagnation tube. Now, how do we go about defining the pressures? Let's start first with the stagnation tube fluid, which has an elevation h2 above its outlet. So using the blue fluid here, we can say that P2 over gamma is equal to h2. In the same way, we can use the static fluid in the second tube, h1, to say P2 over gamma is equal to h1. Finally, if we assume that Z1 is approximately equal to Z2, then we have everything fully specified in our equation. So I can write P1 over gamma is H1, our Z's cancel, and our approach velocity V1 is just V0 squared. Our pressure in the stagnation tube P2 is given by H2 times gamma, so P2 over gamma is just H2, and then V2 is 0 by the second assumption. So what we arrive at is that the approach velocity V0 is the square root of 2g times h2 minus h1. So it looks very similar to the stagnation tube that I included in the follow-up lecture from February 12th. In that case, h1 was 0 in the stagnation tube. Essentially we had a free surface, and so there was no need to have this sort of closed system to measure the differential between two tubes. In a closed system, though, you can't rely on the free surface to provide you a pressure datum, so you use the second tube to do so. And it's the difference between the two heights of rise that define the approach velocity.